basically update parameters of regression system, linear regression system. In linear classification, again, we will be using the same method to update parameters. So the gradient descent method with slight differences in terms of the error classification, the way we calculate the classification error, because it will be used basically the difference between the output of the system and the target output will be used as in the learning rule. So here we have another example, and you can see the difference. We have all categorical data. So we don't have numerical data. So you can see that we have two features, temperature, humidity. The output of the system is binary, class label, so it could be yes or no. So again, it is categorical data. So it's a binary system, that's a binary classification. So the main difference between regression classification and classification is the type of output. So if we are predicting numbers, will be a regression problem. If we are predicting class label, it will be classification. So this is a classification problem. Now, we have, you can see the features are categorical data, so we need to quantify it. Basically, we need to quantify this data in order to update the parameters of the system. So, temperature, we have the first feature, so many samples, so that's the first sample, the second sample, and so on. So every single row is a sample of data. So we have warm, cold, different types. So you can see we have three different categories. So to quantify them, so we can use 1, 0, and -1. Okay? So we need to, basically, the system should work with numbers. So the classification system should work with numbers, especially the input features. So we need to quantify them. So we will assume a value for warm equals to 1. So normal 0, cold is -1. Similarly, we can do the same for the second feature. So we have normal, high, and low. So we have three different categories. So we can assign different numbers. So 0, -1, and 1. So high is 1, normal is 0, and -1 represents low humidity. So we have the size of feature again is, the feature vector is 2. So we have two different features, temperature and humidity. So this is a two-dimensional classification system. So again, if we assume the system is linear, so this is the first feature vector, so it will be 1, 1. 1, 1 means that the first sample. So warm and normal, so warm is 1. Sorry. So the first sample, it should be 1, 1. So warm is 1. So it should be 1, 0. I think this is a typo here. It should be 1, 0 because the first sample so 1 we have 1 normal, so 1 is 1, normal is 0 for the second feature. So 1, 0, and the second sample, so the second sample we have normal, which is 0, and high is 1. So that's the second sample is 0, 1 of the feature vector. So the target output samples, so we have yes, yes, and no. So yes, we assume it's 1, no is -1. So n is the number of samples, so we can have any number, so depending on the availability of training samples. So if we assume the system is linear, that would be the equation of linear system. So relationship between input samples and the output of the system is linear. The objective is to update the parameters of the system. So obviously, as we feed the system with new samples, we update these parameters in order to classify or to learn from the training samples. So this is the meaning of linear classification. So we have in two dimensions, so we can represent the data because we have two features, x1 and x2. We can represent the distribution of data. We have two classes. So in our example, we have two classes. So one class is represented by yes, so class label yes, yes, play football. The second class is, play football, the second class is -1, no, don't play football. So that's two classes. Now we have two classes. Now the problem of linear classification is to find the best straight line that can separate the two samples, the two classes from each other. So we have samples representing class 1 and other training samples representing class 2. Now how we can design a straight line that can perfectly separate the two classes. So once you separate the two classes, then the decision will be straightforward. You will say, if the sample is located above the straight line, the decision is C1. If the sample, so in the when you do the testing, when you test the system, so the decision will be, if the sample is located under the straight line, decision is C2. Okay? So that's why the estimation of these parameters is crucial, because it designs your straight line, the separator, the classes separator. So if it's well designed, so performance will be accurate. So the classification basically will be accurate. So this is how it works. So basically we know we have two classes, because we know from the training samples we have two different classes. We can see the distribution of these samples. The question is to update these parameters. Initially we start with random data, with random parameters. So random parameters could be straight line, like this one. We can have straight line, that's the initial parameters. Now the gradient descent method will adjust the parameters to get a perfect separating straight line. Okay, so initially we start with random numbers for theta 0, theta 1 and theta 2, and then inside the loop we keep updating parameters using the training samples. We update them, which means we are adjusting the parameters, we are adjusting our straight line to get the best separation. Okay, so the best separation means we are trying to find the best classifier that can perfectly classify this set of training samples. It doesn't mean it's going to be 100% accurate on the testing data, but if the test data follows the same patterns, it means we'll get good results. At least it will be reliable, so the system will be reliable. Okay? So whatever the test data is different from the training samples, as long as you've got very good training, the system should be able to get basically high accuracy. So now we have, because this is a two-dimensional system, we have two features, so we can represent it in 2D. So we have x1 and x2. Now if we have three features, we can still represent it in 3 dimensions, space. And in this case, the separating line will be called plane, okay? Because we'll have a space like this room. We can have some samples located in the space here, and the blue samples up. We can have separating line. So this separating line is not a straight line. So we will be talking about the equation of a separating line, plane, not line. In 2 features, this is the equation of the separating straight line. In 3 features, it will be a plane, so mathematically speaking. But in more than 3 features, it's difficult to basically to visualize, because it's just it exists mathematically, but difficult to visualize. So we'll be talking about a hyperplane because we have more than 3 features. Okay? But the principle is the same. The principle is to design a linear system separating plane or hyperplane or straight line, following the same linear equation, so that the parameters allow the system to get perfect separation. So once you design the system, you can see here the decision is straightforward. So you get x1 and x2. Sorry, this one should be x1, x2. That's a mistake, a typo. So once you get new features, if they are greater than 0, it means they are located on above the straight line. So we will say decision is C1. Otherwise, it is C2. Now, the main difference between linear classification and linear regression is the cost function. So the way how we calculate the cost function in order to update our parameters is slightly different. So we'll be using, obviously we'll use the output of the system, but we will define a function or a constant variable called delta x, which is chosen so based on the output of the system. So if the desired output is C1, delta x will be -1, otherwise it will be 1. So it depends on the corresponding desired output for specific sample. So this is an example. So if we have initial parameters theta 0 -1, theta 1 -2, and theta 2 is equal to 3. So the first sample, now if you check the first sample here in the table, so the first sample is, first sample is 1, 0. That's the first sample. So from the table. and the output should be 1. So output is yes, so it should be 1, should be positive. So theta 0 is minus 1. Theta 1 is 0, I think. So if we use x1 and x2 as 1, 1, obviously I think it looks like I think it's yeah, it's 1, 0, sorry. So it's 1, 0. So this is equal to 1, this is equal to 0. So 1 multiplied by minus 2, so it will be minus 2 minus 1, because theta 0 is minus 1. So the output is minus 3, which is less than 0. However, the target output is positive, is 1. So therefore, delta x should be equal to minus 1. The second sample is correctly classified. So if we use these parameters, and the second sample is 0, 1, so we'll get 2. And the target output is 1. So because this sample is currently classified, it will not be included in calculating the classification error. So you can see here, we can only count, the cost function only considers the case where the sample is not currently classified. So the third sample is misclassified. The fourth sample is misclassified as well. So to calculate the classification error from 4 samples, so obviously we'll get minus 1 multiplied by minus 3. So minus 1 corresponds to delta x. And the second one, 1 multiplied by 4. So in total it will be 13. So that's the cost function, which is the classification error, that will be used to update basically parameters of the system. Also, basically used to the classification error is used to is normally used to check whether the system has converged, because normally we will set classification error, so the minimum threshold. If it gets below threshold, then we can stop updating the parameters of the system. Now, the update of these parameters is very similar to what we've seen in the in linear regression. So, of course, we will use delta x. Delta x depends on the target output. So we can either increase or decrease the parameters in order to get the best linear separator. So here we have 2 dimensions, 2 features, so 3 parameters, but if we have n, basically n features, so we will be talking about an n-dimensional linear classifier. So, and all the features will be included to update the parameters from theta 0 to theta 1, theta n, sorry. So basically, if we have so if we have 2 features, So the system should have 3 parameters. So it would be theta 0, theta 1, and theta 2. Now, 3 features would be 4 parameters. So if you have n, so we will have n plus 1 parameters. So n plus 1 parameters to update. So that's the linear equation for m-dimensional system. So if we assume we have m features, so it's basically it follows the same pattern. So we compare the system, so the output, whether it's positive or negative. So we assume we have 2 classes, C1 and C2, where the parameters are calculated using the same rule, not the gradient descent method. Obviously, the key point here is to include delta x, which depends on the target output. So again, it's an iterative algorithm. So we initialize parameters theta 0, theta 1, and theta 2. That's from the previous example. So assuming we have 2 features, we set the target classification error ET. First of all, we need to calculate the output data for the current training input samples. So using this initialized parameters, so we get and then, so we can, from all the samples, we can check the samples that have been correctly classified and all the samples that have been misclassified. So once we do that, we can then calculate obviously the classification error and also update each parameter separately, so using the delta x, because delta x obviously depends on the classification, whether it's correct or whether it's C1 and the output of the system is C2 or and so on. So delta x is the key variable to update all these parameters. Obviously for theta 1 we use the first feature, theta 2 we use the second feature, and so on. The second feature, but obviously different samples. So here is the basically implementation in Matlab. Well, it's obviously it's well documented. So basically, we use a loop. We initialize the training classification error. So we check whether the output of the system corresponds to the target output using the initialized parameters, so theta 0, theta 1, and theta 2. If they are the same, so again, we check if it is class 1 and or class 2, because this is the output of our system. So it's a comparison. Basically, this is class 1, so it was assuming it's the first class, and this is negative, so that's the second class. If there are different, so we define delta x, and then based on delta x, we update each parameter separately. Obviously, to update the first parameter, we will use the first feature. The first feature, but all the samples. So you can see I, goes from 1. So from 1 to length x1. So we go through all the samples. Okay, so we have the first feature, the second feature, possibly the third feature, and so on. So each feature has a number of samples. Okay, so we use all the samples to update the parameter inside the loop. So we can go through this in detail in the lab session. So the implementation and the way how its linear classification performs. We use some existing training samples. So we will try to train the linear classifier on a subset, the training subset. So once we get the parameters, so once we update them, then we take the trained system and apply it to another subset, different subset that will be the testing subset, and then we try to measure the classification error. Classification error means the number of samples misclassified. So to recap what we've seen today, just briefly we've seen a definition of machine learning, what we mean by machine learning, different types of machine learning, supervised, unsupervised, classification, regression, linear classification, non-linear classification. We've seen the difference between supervised and unsupervised learning, the difference between classification and regression. Basically, the main difference is about the output data, whether we are trying to update to predict some class labels, categorical data, that's the case of classification, or we are trying to predict numerical data in regression. Linear classification suggests that the classes are linearly separable, which means, so this suggestion could be true or wrong. If it is valid, so the system can perform well. But in practical applications, not all the problems are linearly separable. Not all the classes, there are some very complicated situations in practice where linear classification cannot work well. So that's why basically non-linear classification is required in most complex systems. So linear classification suggests that the samples are linearly separable. Separator can be represented by a straight line in 2 dimensions, or plane in 3D, or a hyperplane in higher dimensions. Linear regression suggests that the relationship between output and input is linear. Linear means we just use the equation of a straight line. Any questions? Okay, thank you for your attention. If you have any questions, you find difficulty in understanding this talk, please do get in touch with me.